Okay, let's dive right into this explainer and uncover the invisible atmospheric force that dictates whether a hurricane thrives or completely dies. If you've ever watched the weather radar and wondered why some terrifying storms just suddenly fizzle out over warm water, well, you're in the exact right place. Today, we're going to decode a phenomenon that meteorologists watch like hawks, but the general public rarely hears about. Jumping right in, we really have to ask, why do some storms become perfectly symmetrical monsters, while others just totally fall apart? We hear a ton about rapid intensification during hurricane season, but rapid de-intensification, that is just as crucial. Tropical cyclones are actually incredibly fragile beasts. They need a perfectly tranquil environment to maintain their strength. So what happens when that tranquility gets violently disrupted? Let's start by looking at the anatomy of a blob. Meteorologists are tracking some really bizarre, real-world anomalies right now, in July of 2026. Just look at this quote from the forecasting blog, The Eyewall. They described Tropical Storm Bertha in the Gulf of Mexico as, quote, more like a blob, or a couple blobs, or a creepy thing staring at you. It is definitely not that perfect, terrifying spiral we're so used to seeing. Instead, it's just a frazzled, lopsided mess. It's barely holding itself together. But why exactly does it look like a creepy blob? Both Bertha and another system right behind it, Tropical Depression 2, are showing some super strange characteristics. They're acting way more like half cyclones. Their circulation centers are visibly exposed, literally separated from the storm clouds, and practically all of their heavy thunderstorms and wind pushed entirely offshore, far away from the actual center. On top of all that, they're choked by severely limited mid-level moisture. Basically, dry air is just invading them. To figure out why these storms look so deformed, we have to define the invisible force at play here. We are talking about vertical wind shear. Simply put, it's the change in direction and speed of winds as you go higher up in the atmosphere. Think of a tropical storm like a giant spinning top. If you have calm winds at the surface, but raging jet stream winds high up blowing in a totally different direction, well, that upper-level wind literally blows the top right off the storm. It tilts the whole system, unwinds it, and lets that storm-killing dry air rush right into the core. Now, here's a quick but absolutely crucial distinction. We often hear the term wind shear, but there are actually two different types. Horizontal wind shear is when winds change over the ocean's surface, like a strong cold front shredding a storm from the bottom up. But vertical wind shear, which is our focus today, happens at altitude. This is the primary force that tilts a storm's vertical structure and displaces its energy hundreds of miles downstream. Which brings us to a really fascinating phenomenon known as the downshear-left effect. It is just incredible to see how this unseen force shifts a storm's most dangerous weapon, the heavy rain. Let's look at this contour map. It comes from a massive study of over 20,000 satellite snapshots of tropical cyclones. Following it from left to right, you can clearly see that as the wind shear gets stronger, the precipitation completely loses its symmetry. It gets violently pushed to one specific side. It just becomes wildly lopsided. To translate the dense science here, you really just need to remember one simple mantra: downshear-left. When a cyclone hits vertical wind shear, the rain doesn't just scatter everywhere. It's systematically shoved downshear, meaning the direction the wind is blowing, and to the left of that shear vector. That downshear-left quadrant, that's exactly where a sheared storm will mercilessly dump almost all of its precipitation. Let's dive deeper into how this plays out with heavy rain and extreme shear. When a storm encounters extreme, highly destructive shear, the data is honestly staggering. Just look at the number 8. According to the analysis of all those satellite snapshots, when a hurricane is placed under extreme vertical shear, there is a factor of 8 difference in heavy rain coverage. That means the favored downshear left side is getting hammered 8 times harder than the suppressed upshear right side. 8 times. Let's put that into perspective. We're talking 72% heavy rain coverage in the downshear left quadrant, compared to a measly 9% in the upshear right. Plus, the inner core mean rain rates just plummet from about 10.2 millimeters per hour down to 2.7 in those suppressed areas. The rain is also pushed much further away from the storm's center, and this matters immensely for coastal safety. This massive imbalance is exactly why one coastal town might suffer life-threatening flash floods, while a neighboring town just a few miles away gets barely a drizzle. With all this talk of shredded, lopsided storms, it brings up a really interesting question. Does vertical wind shear always destroy tropical cyclones? Is it always the enemy? Surprisingly, no. Experts at AccuWeather point out a really cool exception. Sometimes low to moderate shear acts almost like a sport-tuned exhaust system for a hurricane. In very specific scenarios, a little bit of shear can nudge a storm into warmer waters, or it perfectly vents the system's exhaust high up in the atmosphere, actually helping it spin faster and strengthen. So shear isn't always an automatic death sentence. All right, let's take all this and look at real-world forecasting. Let's apply this hard science to the Gulf Coast right now. Revisiting Tropical Storm Bertha and TD2, they are battling a seriously brutal environment. Their eastern flanks are getting blasted by northeasterly vertical wind shear, while their western flanks are being completely invaded by that hostile dry air we talked about. Because of this combo, rapid de-intensification is expected right before landfall. The storms are being capped at very low intensities, and the forecast models show the heaviest 5 to 10-inch rain totals being kept almost entirely offshore. Thanks to that downshear-left effect, the real-world impacts across the Gulf vary wildly. Notice how the Florida Panhandle and Mobile face locally heavy rain, gusty winds, and flash flood risks. Over in southeast Louisiana, it's mostly squalls and nuisance tidal flooding with a 2 to 4 foot surge. But look at Texas. Because the shear and dry air are shredding the western side of these systems, the Texas coast is entirely shielded. They're expecting hotter temperatures, dry air, and minimal storm impact. It's a downshear-left effect literally playing out right before our eye. Hopefully, this explainer totally changes how you view those spinning blobs on the news. You are now uniquely equipped to look right past a storm center and spot the invisible hand pushing the danger to one side. So the next time a hurricane threatens the coast, will you know exactly where to look?